that lead to this funny stuff like time dilation and length contraction? What are the two postulates that really lead to this?
The law of physics understand all inertial frames, and then the second one, the speed of light is constant in a vacuum, always c.
Exactly, right? And it's especially the second one, that the speed of light does not depend on any relative motion of emitter and receiver. That is really what leads to these funny consequences, like time goes more slowly, passes more slowly compared to a stationary clock in any kind of moving system. And length contraction means if you see something moving fast, you actually see it shortened in the direction of motion. To this, any direction that's perpendicular to the motion, so if I go in this direction, my height and width don't change, it's only the direction in the direction of motion, right? The length in the direction of motion. Okay, so now let's generalize this and derive a general expression of how we can transform any kind of x, y, and z components from one frame into some moving frame. So frame A, we just have x, y, z, and then frame B that moves with a velocity v with respect to this frame. So from classical mechanics, which we now essentially already know is wrong, we have the old classical Galilean transformation, right? Galilean velocity transformation. In which case, well, the most important and the most wrong thing in Galilean transformation is, what about the times? How does the time in classical physics in one frame versus the other frame? Is there any change in the time? No, right? And we already know that's got to be wrong, right? So how does x then transform? X, well, if you are in another frame at some distance x, but now if you're moving away from it, that means the point that you're measuring is actually moving in the opposite direction, right? So it would be x minus t, right? And then, of course, if we're only moving in the x direction, then of course y bar equals y, and z bar equals z, right? Okay, that we can use as a starting point, but we already know that's wrong. So, the first correction that we can make directly, this x here. So, this is the old classical one. Let's contrast that with what we will find. So, what we'll have to derive is the relativistically correct transformation, and those are called Lorentz transformation. So, Lorentz transformations, I mean, the easy thing, what happens with y and z, if we do this relativistically correct now. Any change there? So, dimensions perpendicular to the motion won't change, so this will still be fine. So we have still z bar equals z and y bar equals y. Alright, but now what happens to x bar? We have this transformation, so this is a length in the x direction, length x direction in the other frame. Essentially, we've already calculated that. We know there's simply the length contraction factor that we have to account for. So we have the transformation in x, looking a little more complicated because there's now a Lorentz vector gamma, and then x minus bt. So, and then we also know that something has to happen with the time. In order to calculate what happens to the time, let's first look at this whole situation from frame B. In frame B, this frame A is moving with the opposite velocity, right? Minus v. So in frame B, we can calculate, we can transform into frame A. So we can say that x are transformed from these r coordinates. Of course, this has to be symmetric, right? It's all the same, the laws of physics are the same in frame A as they are in frame B. So now we have another frame moving, but now with minus B instead of plus B. Everything else must be the same. It must look exactly the same. So must be gamma x bar plus B t bar, right? And now we can actually solve this to figure out what t bar is, because we know the connection between x bar and x and t. So let's plug in what x bar is here. So we have x equals gamma, then x bar is gamma x minus gamma t, right, plus b t bar, right? Okay, so this means we can put the b t bar over to the other side. So gamma b t bar is going to be, so we put this here, everything else over, is going to be x gamma squared minus 1, right? Let's bring this over, and that's a minus sign here, and plus gamma b t, right? Okay, so now, first of all, we can, let's just figure out what is gamma squared minus 1. If you look at the definition of gamma here, so gamma squared minus 1 is 1 over 1 minus beta squared, that's the gamma squared, minus 1, or that is 1 minus beta squared, and we have a 1 here, minus 1 plus beta squared, right? So the ones cancel out. There's beta squared over 1 minus beta squared, but we still have 1 over 1 minus beta squared, that's gamma squared. So that is gamma squared beta squared. So let's continue on the other side here. So that means we had gamma b t bar was gamma b t. Did I miss gamma somewhere? Yes, that. Okay, so gamma times gamma is gamma squared. Yeah. There's nobody complaining. So gamma squared bt, and then minus gamma squared beta squared x, right? Okay, first thing, let's cancel out one of the gammas here, one gamma away, one gamma away. There it goes. And let's write a v here, just as beta times c. Right? It's just replacing the definition of v. Okay, then we have t bar equals, well, there was a v here, so that stays there. Gamma t plus here, minus, cancel one of these betas out here, so minus gamma beta x over c, right? We also cancel this here. Well, this is gamma t minus bx over c squared. Plus beta is b over c. Okay, so we have completed our Lorentz transformations here. So the time as we knew already, is not going to stay the same. T bar is going to be gamma T minus dx over 6. Okay, so here we have our complete set of Lorentz transformations. So both we see now that this concept, we knew that already, this concept of some absolute time is no longer there. We know that somehow when you're moving with some velocity, time and space essentially are mixing into each other. So your position suddenly comes into your time measurement, and your length in x direction again has a time component. So essentially you're mixing time and space components. Okay, we can take this maybe one step further and introduce, say, some third frame C here that moves with yet another velocity. Let's call this velocity here B, A, B. That's the velocity between frames A and B. So there's another frame now. Red, another frame here. Let's call this Z double bar, X double bar, and Y double bar. It moves with yet another velocity, V, C in that direction. What's the addition, the total velocity? So if we now calculate with what speed this frame moves with respect to that one. In classical physics, what was the velocity? So in the Galilean transformation, you would have the in the Galilean transformation, non-relativistic, we would simply have that the velocity between frame A and C would just be the addition of the two other velocities, right? Very simple, would be AB plus right? Simply add the velocities up. If you're driving in a car or you're sitting in a train, you're throwing a ball forward, the speed of the ball with respect to the ground is just the addition of the velocities. Right? Do you see a potential problem with that? What could happen if this is really true for all velocities that you add?
You'll have speeds larger than C.
You could, in principle, reach speeds larger than C, right? Like that, 3/4 of C, that 3/4 of C, you would go 1.5 times C, and you see that everything then blows up. We know this time dilation factor here. What if we actually move with the speed of light? Then beta becomes 1. We have 1 minus 1 is 0. We divide by 0. That becomes infinity. That means effectively time stops in whatever moves with the speed of light. Length contraction goes essentially to 0 length. And of course, if beta were to become larger than 1, then simply this becomes imaginary. So it's not a physical figure. So because of relativity has built in this absolute speed limit of the speed of light. So let's figure out what the speed actually is. So if we have one particle moving within frame B with some velocity, so some velocity here that we write as dx bar over dt bar, and compare that to what we measure in x, y, z, t components. Let's calculate what that is. So what is actually the velocity? So assuming something is now moving with this finite speed in x and t dimensions, in the x bar and t bar dimensions. And of course, in this frame, we would measure a higher velocity. Let's calculate what that is. So let's calculate what is dx bar over dt bar. That is dx. We just take the differentials there. dx is gamma dx minus dt, right? So let's be careful. So the v that we're measuring here is the speed. This is the speed AB. Sorry, that's the speed BC. No, so the speed is the speed between frames A and B, right? AB. Sorry about that. And our dt bar is gamma dt minus b, that's speed AB, dx over c squared, right? Okay, so first of all, we cancel out the gammas here, and then just divide everything by dt. So that is dx over dt minus b over 1 minus b dx over dt over c squared. And well, dx over dt is now the combined speed, right? That's the speed in frame A. So this would be our BAC minus BA. B over 1 minus BC over c squared. Okay, or we can write it another way if we are now adding up these speeds VAB and VAC. So here you get essentially a negative boost because frame A is moving negative with respect to B. You can then also say B, or essentially you can just solve this for VAC as well. VAC is first what you would get from the normal Galilean transformation or addition, VC. But then you have this correction term 1 plus VA VC over c squared. And part of this week's homework problems will be to show that this is always less than c. So no matter how large you will choose your velocities AB and BC, you add them up, you will always still end up with a velocity that's less than c. So that's part of the homework to show. Everything clear so far? Any questions? Comments? Okay. If not, then, so let's forget anything from Galilean transformations here, but we keep our nice Lorentz transformations here for reference. So since we're now mixing in time and space components essentially through any velocity boost, you can turn, effectively you can turn time into space, you can turn space into time. That's what this tells you. The logical step is to go away from normal three-dimensional vectors. So for any vector, of course, we have always used x as x, y, and z. But now it's becoming obvious that time kind of takes a very similar role to these space components, right? So what we'll do is actually turn this time component into something that's also a length, namely we just multiply by the speed of light. Then all four components are length. And of course we have this here, that's 1 over c here, which of course b over c is our beta, right? So it's gamma ct minus beta x. And what we're now doing in our generalization is use a 4 vector. I always denote 4 vectors by underlining them. So distinguishing 3 vectors just with the arrow on top, 4 vectors, x with an underline. So this is now a four-dimensional vector with Ct up here in the time component, the 0 component, and x, y, z. And typically we give this the index 0, 1, 2, 3. So we write x as x0, x1, x2, x3. And in a moment it will become clear why I'm writing this in a funny way that I write the index up, not down. That will actually help us with the notations. Okay, so that means we're introducing the zeros component of our vector, which is simply c times 2. So from this, we can also see that x0 Lorentz transformed is just gamma x0 minus beta x1. This transformation tells us x1 bar is gamma x1 minus beta x0, right? Because beta x0 is beta ct, beta c is v is the velocity. So that's what we have. All right, so now we can actually write this in a more compact way with a matrix. So we have one vector here, we have a vector x bar, we know how these are transformed. We can actually write this as x bar for vector as some kind of matrix lambda times x. First of all, what kind of matrix would this be? How many entries does that matrix have to have? It's a two-dimensional matrix, right? Vector times matrix gives us another vector. Has to have 4 entries, so 4 by 4, so there must be 16 entries in there, right? Okay, so what's the form of this matrix lambda? So we can write this out. So that means this is equivalent to x0 bar, x1 bar, x2 bar, x3 bar equals our entries lambda 0, 0, lambda 0, 1, lambda 0, 2, lambda 0, 3, lambda 1, 0, lambda 1, 1, lambda 1, 3, lambda 2, 1, lambda 2, 2, lambda 2, 3, and lambda 0, 3, 1, 3, multiplied onto x naught, x1, x2, x3. So how does matrix multiplication now work? Essentially, flip this over, multiply on to every line. Right? So you get x naught, lambda naught naught, plus x1, lambda naught 1, and so on. That gives you your 0 entry. The second, so x1 bar, x naught 1, 0, x1, 1, 1, x2, and so on. Right? So if you can just to clarify this here. Yes. And so what we have there will give you vectors of x naught lambda naught plus x1 1 plus x1, and then you have x naught 1 0 plus lambda 1 1 plus x1. Right? Okay, that's the vector that comes out. So now we can compare. So what does lambda look like? What comes in? So we have our zeros line here. X0 comes in with a factor gamma. X1 comes in with a factor minus gamma beta. So this diagonal element is a lambda 0, 0. This is gamma. Lambda 0, 1 is minus beta gamma. What are the other two entries here? Are y and z coming into a new time. So what are the other entries? Zeros. All zeros. Exactly. 2 zeros. Very good. Now for x1, the second line there, there's a gamma coming in for the x1 as well. That's this one here, right? Again, no y and z come in. And the time comes in with minus gamma beta. The x0. Minus beta gamma. Okay, and for y and z, so x2 and x3, what do we have? They don't change, so that means the matrix is just diagonal ones. So 0, 0, y, only the y goes over directly, and 0, 0, right? So this is our, we can call this lambda mu, mu. So with entries mu and nu being between 0 and 0, 1, 2, 3. Okay, so now we do a little bit of simplifying the way we write things here. Let's pick out one index mu that can be x0, x1, x2, or x3. Well, actually what we have written here, what I had here, is that this is just the sum over the x components of the other vector. Right? So we sum all the u's from 0 to 3, 0, 1, 2, 3, over these lambda u x u. Okay. It's simply a shorter way of writing this. And now we're doing an even shorter way of writing the exact same thing. So we're not doing any physics, we're just saving a little bit of writing effort. If we write this as lambda mu x nu, we essentially define this. If we have the same index here as upper and lower indices, then we simply define this as summing over it, and this is a convention that's called Einstein's summation convention. We haven't done anything. This simply means the same thing as that. So if we write this lambda mu x nu, that means we just sum lambda mu 0, lambda mu 0 x 0 plus lambda mu 1 x 1 plus lambda mu 2 x 2. That's really just what this means, only just to save a little bit of writing. Does that make sense? Questions? See the rain weather really got you. Okay, good. Then, all right, so now let's see if there's any more meaning to this 4-vector concept. And one thing with the 4-vector concept now, that we see really that time and space are more or less on equal footing in terms of being transformed into each other through a velocity boost, through a Lorentz boost. Okay, let's look at a somewhat different angle. In classical physics, if you do a Galilean transformation or any kind of transformation, say you have the x, y, and z coordinates of the beginning and the end of the stick, you can move this somewhere to another place, you can rotate it, do anything. Of course, all kinds of coordinates will change. What is it about the stick that does not change in classical physics? Exactly, the length, right? So in non-relativistic physics, well, the length is really just delta x, right? And take the square root of it. Right? So it's really just, that means effectively if you have, say you define your coordinate, the 0 point of your coordinates at one end of the stick, you can essentially say that x squared plus y squared plus z squared will remain constant, right? So that's the length squared is constant. Okay, so no matter what you do in classical physics, if you move it with a non-relativistic velocity boost or you rotate things, this will not change. Is that still true for our Lorentz transformations? Definitely not, right? So if we now say x1 squared plus x2 squared plus x3 squared, compare that to the bar quantities, well then we have this nasty factor there, that is gamma squared x1 minus beta x0 squared plus, just write y squared. That's the same, of course. But generally we can already say that this is not going to be x1 squared, right? So something gets messed up. And effectively, that's what we already know because we have calculated length contraction. The length is not going to stay the same. But well, we didn't really expect that because we now have 4 dimensions here. What if we maybe add here an x0 squared into that? What do we get then? So then we get plus gamma squared, that is x1 as x0 minus beta x1 squared, right? Let's see what that gives us. That gives us gamma squared x1 squared minus 2 gamma squared beta x0 x1 plus gamma squared beta squared x0 squared plus, so let's, no, nothing happens in y and z, so let's just forget these 2 components for now, right? We know they're not changing anything. So let's see, that plus gamma squared x0 squared minus 2 gamma squared beta x0 x1 plus gamma squared beta squared x1 squared. And we can already see that pretty much no matter what we do, we